Okay, here we are in section 7.2. We're going to look at the describe the variation of our shear and moment along the whole length of the beam as a function of x. And I start out by looking at our free body diagram here, looking at a mostly focusing on our reactions. I wanted to calculate what the reactions were. So I can draw a cut, an arbitrary cut. So if I cut the beam somewhere, not necessarily the center, but just somewhere, I make an arbitrary cut so I can analyze the internal stresses. So here's our cut. Call this C. So here's our section C cut. So then let's fill in the rest of the loads here. We have a reaction here of 9. We're going to have a shear force. I'll just draw these positive cents. We'll have a normal force. And we will have a moment, a bending moment. And then, of course, I have to take into account this distributed load. Now, since this is a cut in the direction x here, the load varies as a function of x out to a maximum of 6 kilonewtons per meter. So what I need to do is I need to figure out what this W of x is. And W of x is going to be the equation of this load, and it's linear. It starts at 0 and is linear and goes to, at the end, 6 kilonewtons per meter over 9. So essentially what we're going to do is we're going to look at the rise. We've got to figure out the slope of the line, rise over run, times x plus b. That's a slope-intercept form for a line. But b is not necessary since we started at 0 over here. So this then is going to equal, the rise is 6, so we got 6/9 x, which ends up equaling 2/3 x for W of x. Well, if that's what W of x is in our little triangle here, and the distance is x, then if we think of a triangle that is shaped like that, where the height is 2/3 x and the width is x, then our area of our triangle equals 1/2 times 2/3 x times x, or 1/3 x squared. 1/3 x squared is the area of this triangle, and that is going to be then the value of this load P. So therefore P equals 1/3 x squared, and it's going to occur at a distance of, if this total distance is x, then this must be x over 3 here, where this is applied from the cut. Okay, I guess I wasn't recording, so what we're going to do is, so we take the triangle load here, our distributed load is in shape of a triangle, and we look at it, and it's over a distance x with a height of 2/3 x. So the area of that is 1/3 x squared, and that equals P, the value of our concentrated load that we place here. I don't know if that was recorded or not, so I just repeated it. And that is placed at a distance of x over 3 from the left edge here. So next I'll just sum forces in the x direction, set it equal to 0. That's going to equal 9 for my reaction, minus v for my shear force, and then also minus the x squared over 3. So we have just come up with an equation as a function of x for v here, because I can solve for v, and that equals minus x squared over 3 plus 9, and that is v of x. V is a function of x. Now if I stick that in a plotting program, I use Mathway here, you can see that at 0 this is 9. Let's use a bright color. At 0 this is 9, a value of 9, and then we cross the value of shear. So this is our shear diagram. So shear is the y-axis, and the x-axis is distance along our beam. That as we get to 9, so this is the edge of our beam here, we are down at this point here, which is minus 18. And you'll see that corresponds with the endpoints correspond with our reaction. So if we were going to draw by hand our shear diagram, we would draw it like this, hand drawn. Now it won't necessarily look to scale like the plot over here, but it will contain all the information we need. So here we go up to 9. So we push up to 9 because of the reaction. Then we head down 1, 2, 3, 4. So down to 18 over here. We cross somewhere around here. And this is a second order function. So this is minus 18. And now when we hit this point, we can push up. So this is a plot of the shear diagram. And it represents the internal shear that is experienced in our member. And it makes sense. So there's more shear forces here towards the roller bearing end, where the load is the highest, which means that if this beam was going to fail in shear, that's the highest point over here. It's going to fail over here on this edge. Okay. All right. So we are interested in where this crosses. That's an interesting point, where this crosses where v equals 0, and we can figure that out. We can calculate that because we can set v equal to 0 here and solve for x. So minus x cubed over 3 plus 9, x squared, not x cubed. And we're only going to be interested in the positive value of that. So x squared equals 27. Therefore, x equals the square root of 27, which is 5.196 meters. So this occurs at a distance then of 5.196 meters. All right, so let's now find an equation for our moment. And so we'll sum our moments about the cut equals 0. So the cut is right here where we cut this. And this equals, well, we have this 9 rotating in a negative sense. So, of course, we'll put this on here. Oops, let's put this the other way. Positive this direction. So minus 9 times the distance to the cut. Well, the distance to the cut here is x. 9 times x. And then we have plus p, which is 1/3 x squared. Oops, we don't want to put that in parentheses, do we? Stick with our convention of the moment arm in parentheses times x over 3. And then finally we have minus m. We got to include that because it is a free moment. So we can say that our moment equals actually, as I'm looking at this should be positive because it's spinning in the positive direction. So moment equals minus x cubed over 9 plus 9x kilonewtons meters. And that is our equation for our moment. And here's a plot of that function. So I could notice that this maximum point will occur actually ends up occurring at the point where the shear force is the smallest, and so we can calculate that. The maximum or the moment at 5.196, that is where this shear is 0. This ends up equaling approximately 31.2 kilonewton meters. Now, something interesting here, if we were to take our moment and differentiate it with respect to x, so again, this is our x direction, and this is the value of our moment along here. But if we were to take this and differentiate it, we're going to get minus 3x squared over 9 plus 9, which equals minus x squared over 3 plus 9. And lo and behold, what does this equal? This actually equals our shear. And we're going to investigate this further in the next section. Now, it's important to know where your maximum moment is when you're designing things like beams, because the maximum moment, which occurs somewhere around just past this midpoint, is where you're going to have your maximum stresses in your beam, your maximum flexural stresses in your beam. So it's important to know where that is so you can design your beam accordingly.